Hey everybody, I hope this video finds you well. In today's video, we're going to be continuing on with a couple more examples of the very first hypothesis test that you guys have learned, which is the one sample mean hypothesis test. We're going to do a couple examples here, running through those 5 main steps of the hypothesis test, with a special focus not only on just performing the computations and getting more comfortable with this procedure, but also paying special attention to sort of how we interpret and write the conclusion of a hypothesis test. So let's go ahead and jump right into this first example here. So, that should be in the laser pointer there. There we go. So our first example. So we're going to suppose you work for a community college with around 15,000 students. The college found out that in the previous semester, the average round-trip commute for its students was 62 minutes. Since that semester, the college has worked on scheduling its classes at different times to avoid peak traffic hours. So you are tasked with determining if this has been effective at lowering the average commute time. So the idea here is that by scheduling this classes at different times, right, hopefully this can lower the amount of time that the students spend commuting. So to study this, you select every 20th student that enters the student union building on a particular day. You ask each of these students for the length of their round-trip commute. You end up talking to 16 students, and you get the following data with all the values being in minutes. So there's our data right here. You can see somebody had a round-trip commute of only 26 minutes, somebody said 32 minutes, so on and so forth, all the way down to one of the people that said 83 minutes. So we're going to do a couple things with this. We're going to talk about what sampling technique was used here. So that's just a sort of purely review question. Then in part B, we're going to carry out at alpha equals 0.05. Remember, that is what we call the level of significance. We'll carry out a hypothesis test to test the claim that the average commute time for students at this college has decreased. So we're going to see if this group of 16 students gives us enough evidence to believe that the average commute time has actually decreased. And then at the end, we'll talk about the type 1 and type 2 errors in this situation. So let's go ahead and start by talking about the sampling technique. So for the sampling technique, right, we have a couple different sampling techniques that are available to us. We know we have that SRS, we have the stratified, we have the cluster, we have systematic. So in this case, let's think about how the sample was built. We can see here that it said that to study this, you selected every 20th student to enter the student union building on a particular day. By using every 20th student, that is an example of a systematic sample, right? And the system was every 20th student. Okay, so there we go. We know the sampling technique that was used. It was a systematic sample, which is a valid way of doing statistical sampling, and we know it's systematic because we used every 20th student. Okay, well, let's go ahead and move on to part B then, running the hypothesis test. Now, what type of hypothesis test is this? Well, we only know one type, so we better hope that it's a one sample mean hypothesis test. Well, let's see if that's true. First of all, let's look at our data. How many samples do we have? Well, we talked to 16 students making up a one single sample. What was that sample? What sort of data was that sample? Well, you can see that everybody in our sample provided a value, a quantitative piece of information. So we have a single sample of quantitative data. Do we have an average that we're going to be comparing it against? Well, we know that the average commute time in the previous semester was 62 minutes. So we have one set of quantitative data, and we have a known or assumed average to compare it against. So that is exactly what a one sample mean hypothesis test is supposed to be. So one sample quantitative data versus known/assumed average. Okay, so that's exactly what the test that we've learned so far is useful for. So let's go ahead then and get started with it. So first step we need to have here are our hypotheses. So we know that for a one sample mean hypothesis test, the null hypothesis and the alternate will be of the form mu equals some value, and the alternate will be mu with some inequality sign and that value there. Two things to do here. First, we need to fill in, this value, and we also need to figure out the inequality sign. So let's think about what this null hypothesis is. What is the known or assumed average? Well, if in the previous semester the average was 62 minutes without any other information, if it was 62 minutes in the previous semester, we think it would be 62 minutes now. So the known or assumed average here is going to be that 62 minutes. So we're going to have mu equals 62 and 62 there. Remember, the alternate hypothesis is our claim. You can go back and read B again to remember what the claim is. The claim says that we want to know if the average commute time for students has decreased. So we want to know that if it has decreased or gotten lower. So our claim here is mu less than 62. We're saying without any information, we're going to assume that it is 62, but we'd like to see if there's evidence that it is now lower than 62. Remember that since we did this as less than here, that is a particular direction, so we would call this a one-sided test. And when we get to step 4, the p-value, and we go on to table C, we will look at the one-sided p-value to correspond to the one-sided test. Okay, let's go ahead and talk about the conditions then. So, first condition is that the sample is supposed to be random and representative. Well, we can look through here and see if we see any mention of the word random. Unfortunately, there isn't, but we do have to remember that a systematic sample counts as random. So all we need to do here is we just need to remind ourselves that systematic counts as random. So we're all good with the random and representative. Again, with that second R being representative, that's not something we're going to worry too much about in this class because, again, with the limited information that we're given in an individual problem, there's really no way whether we can diagnose the representativeness. So all we really care about is making sure that it is least valid for statistical analysis, which means it must be random. And since we did a systematic sample, that counts as random. We're all good there. The second thing that we need to check is we need to check if our sample size is less than 5% of the population size. Now, in every case, we're going to know our sample size. What was our sample size in this case? Well, we know that we talked to 16 students, so that's going to be our sample size. What about the population size? In the last example, in the previous video, we didn't know the population size because we were studying something like the jars of peanut butter produced by a company, and there was no way we knew how many there were. But actually, in this case, if we read back through here, we actually do have some information about the population size. We are looking at the students at this community college, and we know there's around 15,000 students. So this right here gives us our population size. So we can actually check if our sample size is less than 5% of the population size. So we can directly check n equals 16. Is that less than 5% or 0.05? Times the population size, which is 15,000. Well, if you do that on your calculator, you can just directly confirm 15,000 times 0.05. That should be 750. And very obviously, 16 is less than 750, so we're all good. In other words, we're saying that we could have taken a sample of up to like 750 students, and we would be safe in saying that our sample would be less than 5% of our population size. Notice at this time we really did have to actually check something here because the problem gave us some extra information, namely the population size. Okay, let's go ahead then and look at condition 3. Remember, condition 3 says that the data is either approximately normal or n is greater than 30. Last time we did this, in the previous video, the n was larger than 30, so we were able to say that. This time, that is definitely not the case. N is only 16. So we're going to need to directly check if the data is approximately normal. Okay? So let's do that over here. What's the easiest way to check if the data is approximately normal? Well, we have access to the raw data here. Let's do a visual display. You could do something like a histogram, but it's probably easier if you just look at the data instead of building classes and measuring the frequencies to just go ahead and do a stem and leaf plot. So let's go ahead and do that. Our stems would be 2, 3, 4, 5, 6, 7, and 8. Certainly no need to split the stems because even without splitting, we've got 1, 2, 3, 4, 5, 6, 7 different stems, so there's no need to do that. And we've got 26, and we've got 32, 43, 44, 50, 51, 52, 56, 58, 60, 61, 64, 68, 71, 75, and 83. And we need to look at this guy. Of course, we should probably include our key, right? Our key here, 2/6 is actually 26. Well, what are we looking for in this? Well, we're hoping that the data is roughly normal. Does this thing look roughly normal? Well, if you turn it on its side, does it show basically a bell shape? Well, you should be able to see that because if we look at this thing, right, it's sort of, if we imagine it sort of like a histogram, right, that guy right there, that definitely looks like a bell shape. To be honest, what you're really looking for is you're making sure that there's no strong skew. Check. I mean, there's a little bit of a skew, right? Things pile up here, right? And there's a little bit more of a tail out this way than this way, but it's not a strong skew. And most importantly, there are no outliers. That's the main thing we want to make sure about. The reason that it's so important that there are no outliers is because we're testing something about the average. And as you guys learned at the very beginning of this course, right, if there are outliers, the average can be greatly impacted by that because it's a non-resistant measure. So it's super important when you're doing this analysis that there are no outliers in your data. And we can see that just by simply noticing that the largest and smallest are very close to the rest of the data. So we're all good there. Okay, so a bit more work to do all the conditions here, but we got all that done. Now we're ready to move on to step 3, the test statistic. So we'll do that on the next page here. So for step 3, we need to go ahead and get our test statistic. So remember that the formula we'll be using here is t equals x bar minus mu over s over root n. This is always the test statistic associated with a one sample mean hypothesis test. To do this, we need to know 4 things: x bar, mu, s, and n. Well, if we go back, we've already found a couple of these things, right? If we go back over here, we know that the mu was 62, and we know that the n, the sample size, was 16. So let's go ahead and record those. So we know that mu is 62 here, and we know n is 16. What's missing, though, is the sample average and the sample standard deviation. If you think back to the previous video, last time we got these by reading through the problem and finding that the average of the sample and the standard deviation of the sample was given to you. This time, though, if you read through there, there's no mention of the average or the standard deviation of our sample. But we don't need that because we have the raw data. We have the 16 data points in front of us. So all we need to do is take these 16 data points, right, as we would standardly do, pop those into L1, and then go ahead and do 1 var stat and record the mean and the standard deviation. If you do that, I think I already have mine in, so it should be pretty quick. Let's see. Yep, got our data in there. 26, 32, 43, 44, 50, 51, 52, 56, 58, 60, 61, 64, 68, 71, 75, and 83. You can go stat, calc, 1 var stat, and we'll record these things over here. Should get a mean of 55.9. So the average in our sample was 55.9 minutes. And it looks like the standard deviation, of course, use the sample standard deviation because it is a sample, is 15.1. So we can basically see what we're really trying to do here. The average for our 16 students was 55.9. That is certainly below 62. We're saying, is 55.9 far enough below 62 to believe that since we only talked to 16 people, there actually has been a shift overall on the campus? Or is this something that's well within the sort of range of normal sort of deviation or variation? So to do that, we got to actually calculate the test statistic. So for t here, we get 55.9 minus that 62 over 15.1 divided by the square root of 16. Good idea to go ahead and do top and bottom separately here. So 55.9 minus the 62. You should get negative 6.1 up top. And then 15.1 divided by the square root of 16. Looks like we should get 3.8 in the denominator, and then go ahead and do that division, and you should get that t is approximately negative 1.61. So there we go. We got our test statistic. Notice it makes sense that we got a negative test statistic because we are trying to see if the average has gotten smaller or if our sample is below the average. And in this case, they were saying it's about 1.61 standard deviations below the average. All right, we can now get ready to go ahead and get our p-value. So for the p-value, we'll need to use table C. We need to use table C because we have a t-test statistic, and whenever you have a t-test statistic, you need to use table C. For table C, we need to know the degrees of freedom. Remember, degrees of freedom in this case is always the sample size minus 1. So we'll be using 16 minus 1 equals 15. If you also think back to the previous video, we made a comment or a note that said that if you ever get a negative test statistic, you will need to think about it as the absolute value. So when we go to look for table C, we will be thinking about t as 1.61. We still record t as negative 1.61, that's its actual value, but when you look at the table, you'll be thinking about it as 1.61. So our t is 1.61 and our degrees of freedom is 15. Let's go ahead and take a look at the table. So there's our table. There's our 15 degrees of freedom. There's our previous one there, but that's okay. I think that was from the last example, so I copied that over. Okay, so this time our degrees of freedom, I'll put this in blue here. Our degrees of freedom is equal to 15. I'm just going to cross this out because we don't need it this time. Okay, so we'll be using this guy right here. Remember, our t-value was 1.61, so we should find ourselves right in there, in between the 1.341 and the 1.753. So we'll follow that down to here, and we should find ourselves right there. And again, I'm going to just cross that out, because we don't need those. Okay, so we should find ourselves right there, and of course we are using the one-sided p. So that tells us we're in between that 0.05 and the 0.10. Remember, this is always the low end, this is always the high end there. So our p-value is somewhere between 0.05 and 0.10. Okay, let's go back and take a look at that. So we just figured out here that our p-value is somewhere in between 0.05 and 0.10. Okay. So we looked up our t-value on our table C, and we found that our p-value lands somewhere between 0.05 and 0.10. Remember, what this is basically telling us is that the probability that our sample occurred basically by random chance is somewhere between 5 and 10%. Okay. All right, let's go ahead and make our conclusion here. So we want to compare the p-value against the alpha of 0.05 that was set for us in the problem. So how does this p-value compare against an alpha of 0.05? Well, we don't know the exact p-value, but we know it lands somewhere between 0.05 and 0.10. Specifically, we know the p-value is larger than 0.05. We don't know exactly what it is. It could be something like 0.06 or 0.07 or 0.08 or 0.09, but any of those is certainly going to be larger than that alpha of 0.05. So in this case, the p-value is going to be larger than the alpha of 0.05. What conclusion do we make when the p-value is larger? Well, this is where we will fail to reject HO. So, in other words, we're failing to throw out our original assumption. Whenever you fail to reject HO, you should immediately then say no significant evidence for whatever our claim was. In this case, our claim was that the average commute time has reduced. So there's no significant evidence that the average commute time for students has decreased. That's our conclusion there, right? We have no significant evidence that the average commute time for students has decreased. Now, you might say to yourself, well, wasn't our sample a decrease? I mean, didn't the people in our sample have a lower average? They absolutely did, right? Their average was 55.9, which is certainly lower than 62. But what we're saying is that 55.9 isn't that far below 62, especially considering it was only for 16 people, that is not enough evidence to convince us that this has really decreased for everyone. It could have decreased, but we don't have enough evidence to say that. In other words, this isn't enough for us to be convinced. And that's what our conclusion right here is really telling us. It might be that there's been a decrease, but we don't have enough evidence to really believe that. So whenever you fail to reject, you should always say no significant evidence for whatever your claim was. Okay, so we went ahead and did another example of running through one of these one sample mean hypothesis tests. Let's just quickly go back over the pieces. Remember, For our hypotheses, we set those up. One of the differences here from the first case we did for the first example in the previous video was that we had a decrease here because we were talking about that the average has gone down. We had to do a bit more work in the conditions in this example. Specifically, we had to realize that systematic counts as random. Because we were given the population size, we actually had to manually check this through a computation. And since we had the raw data and a relatively small data set, we actually had to check whether or not the data was approximately normal. Once we had confirmed all those conditions, step 3 should feel very similar to what we did in the first example. Same thing with the p-value. Only trick with the p-value in this case was remembering that since we had a negative t, we had to use the absolute value. And then the conclusion, well, that part always the same. If the p-value is greater than alpha, you fail to reject, which means you have no significant evidence. If the p-value had come in less than alpha, we would have rejected HO, and we would have had significant evidence. Okay. We had one more thing we wanted to do with this example, so I'll just draw a little dividing line there in part C. We wanted to talk about the type 1 and 2 errors. So again, whenever you're going to be discussing the errors, you should just probably, it's a good idea to go ahead and remind ourselves what the hypotheses were, because the errors are based on those hypotheses. Remember, our hypothesis here was that the average is still the 62, and our claim was that the average has decreased from 62. So let's think about what the type 1 error would be here. Remember, in general, we'll use some colors to do this. The type 1 error is when we say we reject HO, but HO is really, but we'll say it this way, make it a little clearer there, HO, but in reality, HO is true. So remember, a type 1 error, which often is called a false positive, is where we decide to reject HO, but in reality, HO is true. In this case, rejecting HO would mean that you were throwing this out and going with that there has been a decrease. So this is where we would say we believe there has been a decrease in average commute time. Okay, that's what the rejecting HO part would mean. But in reality, well, what does it mean for HO to be true? That means this is still the case. But in reality, the average commute time is still 62 minutes. So this is the type 1 error here. This is where we believe that there's been a decrease in the average commute time, but in reality, the average commute time is still 62 minutes. In real life, what would be the sort of mistake here? Well, this is where we would be thinking that that change in how we scheduled the classes really did help, but it actually didn't help, and people are still taking the same amount of time to commute. All right, let's go ahead and talk about the type 2 error. Type 2 error, right? This is where the conclusion we would make is fail to reject HO, but in reality, HO is false. So, failing to reject HO, that means we don't believe that there's been a decrease in the average commute time. In other words, we don't think that there's any evidence here. So, this is where we would say we believe there is no significant evidence for a decrease in average commute time, but in reality, well, what does it mean for HO to be false? Well, that means that really is wrong and there has been a decrease. But in reality, the average commute time has decreased. Okay. Now, what's the real life consequence of this? Well, this is where we decide that this new scheduling hasn't helped, but it really did help, right? And you could imagine that this would be sort of a risk because if we decide that it hasn't helped and maybe we revert back to the old way of scheduling, we lose that benefit here. But you can imagine why, again, the type 2 error is called a missed effect, right? Because what is happening here is that we don't think it did anything, but it really did help in terms of decreasing the average commute time. Now, one last thing I want to point out, in all of our conclusions, back from here when we made the conclusion, and when we talked about the types of errors, which of course naturally have a conclusion in them, make sure you're aware that every time I'm writing in that word average, because again, that is what this hypothesis test is testing. It's testing something about the average. It's not about individuals, it's about the average. Okay, so let's go ahead and take a look at one more example of running this procedure here. All right, so for this example, we're going to say, according to a study from 2016, American adults spent on average 135 minutes per day using social media. You want to study if that average has changed, right? It's now 2020, and we want to know if that's changed. So to study this, you randomly select 101 adults from across the country, and you study how long they spend on social media per day. You find that your sample has an average of 149 and a standard deviation of 59. So we're going to carry out at alpha equals 0.05 a hypothesis test to test the claim that the average time spent on social media per day for American adults has changed since 2016. And then we're going to do a little bit of error analysis, but we're going to sort of do our error analysis in reverse. Instead of trying to write out the type 1 and type 2 errors, we're going to try to decide if we made the decision that the average time spent on social media per day for American adults has changed, when in reality it has not changed. Would that be a type 1 or type 2 error? So instead of writing out what both errors would mean, we're going to try to determine what error is being described. So it's sort of the reverse. Those are sort of the two main ways you guys are usually quizzed or tested on how to think about errors. But let's start off with talking about part A, actually running the hypothesis test. So for part A, this is again going to be a one sample mean hypothesis test. How do we know that? Well, we sampled our 101 adults, so we built one sample. We studied how long they spent on social media per day, which is, of course, a quantitative variable. We know it's quantitative because we calculated things like the average and standard deviation. So we have one sample quantitative data versus, well, do we have a known or assumed average? Well, we have this work from 2016, which is what we're going to assume is still the case. So we have a known or assumed average. So versus a known / assumed average. So it is definitely a one sample mean hypothesis test. Okay, so let's go ahead and start off with our hypotheses. So for the hypotheses, we know format-wise, it's going to be mu equals, and the alternate is going to be mu with some inequality sign and that value. First thing we should try to do is fill in that value. That's going to be whatever our assumption is. And of course, if this was the case in 2016, then we would think that without at least any other evidence, it's still the case today. So our null hypothesis here is going to be that 135, and we put that in both spots. Then we need to think of the inequality sign. Remember, that should always be based on your claim. What was our claim here? Well, we're trying to claim that it has changed. So we're not claiming that it has gone up. We're not claiming that it's gone down. We're claiming that it's changed, meaning it simply is not 135 anymore. So we will use a not equals to here, and this will be our first example of running a two-sided hypothesis test. In general, you guys should get very used to the words like changed or is different for identifying two-sided tests, because if you say something has changed or something is different, you're not giving a particular direction or a particular side. You're really doing a two-sided test there. Okay, let's go ahead and check the conditions here. Okay. First condition, random and representative. Well, this time it's a bit easier. We see that they said that you randomly select those 101 adults. So it's stated right in there, and we're all good. 2, we need to think about our sample size and decide if that's less than 5% of our population size. Well, sample size, that's something we always know. That's the 101 adults. Population size. Well, last time we got sort of lucky because we knew how many students there were at this college. This time we're studying American adults. We definitely are not given in this problem the approximation of how many American adults are out there. But we certainly know that there's tons and tons, so there's no concern about this. So all we would need to say is lots of American adults there is no way that our sample of 101 represents some large percentage of the American adult population. So we just say lots of American adults and we're all good there. For step 3, right? Well, do we need to do a stem and leaf plot? Probably not, well, especially since we don't have access to any raw data here. Instead, we're just going to rely on our sample being larger than size 30. So we'll simply say n is 101, which is greater than or equal to 30. So we're all good. All right, now we can move on to step 3, our test statistic here. For our test statistic, let's look at t being x bar minus mu over s over root n. So we've got 4 things again that we need to know here. Keep in mind we've already written down mu equals 135, and we've already used that n, which is that 101. Only thing that remains is the sample average and sample standard deviation. Well, we look back up and we find that your sample had an average of 149, standard deviation of 59. So we'll go ahead and use those. This will be 149 and this will be 59. So we throw those values in there, 149 minus 135 over 59 divided by the square root 101. Again, probably a good idea to do top and bottom separately. We get 14, and then in the denominator there, we get 59 divided by the square root of 101. Looks like we should get 5.9. And I suppose then we can just take that all the way back up here. So we get t approximately, our calculator, 14 divided by 5.9, 14 divided by 5.9, looks like we should get about 2.37. So what that's saying is that getting a sample of 101 adults who had an average of 149, that is about 2.37 standard deviations above average, given our expectation that they should have had an average around 135. Okay, let's go ahead and get our p-value from here. We're going to need to use table C, and our degrees of freedom here is going to always be that n minus 1. So 101 minus 1 equals 100. Okay, let's go ahead and take a look at that. I think I had that's marked, so we'll do this in green here. So let's go ahead and look for that. We've got 2.37 as our test statistic and 100 degrees of freedom. So we have 100 degrees of freedom here. So we'll be using this guy right there. We had 2.37 as our test statistic, so we make it in just right over here. So we'd be right there. Oh, sorry. We should write that in as 2. Oh, no, we had 2.37. Excuse me. So we actually don't make it over that. We have 2.37, so we're slightly less than this guy here. Yep, 2.37. So yeah, we land right there, just a little under that 2.374. And that means when we go down here, this time we will be going down to the two-sided p. We will find ourselves right here, and we will see that our p-value is somewhere in between 0.02 and 0.04. So let's go ahead and use that. So we found that our p-value in this case, 0.02, is less than that p-value, is less than 0.04. And again, remember when we go to write this, we always reverse it because the low end is actually on the right and the high end is actually on the left. So you got to reverse it when you write it to make sure that this inequality makes sense. So we know that our p-value is somewhere between 2% and 4%. What again that means is that if this null hypothesis is really true, in other words, that the average is still 135, the chance that we would get a sample as or more extreme than the one we did where people had an average of 149 is between 2 to 4%. So we now go ahead and make our conclusion. So we take this p-value and we compare it against the alpha that was given. Notice pretty much always we're using alpha 0.05. In later videos, we'll talk about some other options, but again, this is always just stated in the problem, and 0.05 is very common. All right, there's our p-value. We don't know exactly what it is, but it's somewhere between 0.02 and 0.04. Certainly, if it's less than 0.04, it is also less than 0.05. So we know in this case, the p-value is less than 0.05. So what can we say then? Well, when the p-value is smaller than the alpha, this is where we decide to reject HO. All right, rejecting HO means we did find evidence. So we have significant evidence for whatever our claim was. And remember, our claim was that the average has changed. So, significant evidence that the average time spent by Americans on social media has changed since 2016. Now, you might say, do we have evidence that it has increased since our sample was higher? Well, that's not what we were running our test for, right? So this conclusion is specifically based on how we phrased our test. And we phrased the test as whether or not the average has changed. So that's how we have to phrase our conclusion here. So we'd say that there's significant evidence that the average time spent by Americans on social media has changed since 2016. So we've basically decided that this sample was far enough away from this, despite it was only 101 people, that we're convinced this is true for the overall population. All right, so this one went a lot faster than the previous, not only probably partially because we're getting more comfortable with it, but also because in the conditions, things went a lot faster since the population was absolutely massive, American adults, and the sample size was large enough that we didn't have to actually check the normality. So this part went a bit faster here, and hopefully you guys are getting more and more comfortable with the calculations in there. Let's go ahead and briefly talk about part B as well. In part B, we're saying, would deciding that the average time spent on social media per day for American adults has changed since 2016, when in reality it has not changed, be a type 1 or type 2 error? So, in other words, would this be a false positive or a missed effect? So let's read through this. We're saying we decide that the average time has changed. So we think something has happened when in reality it hasn't. So we think something happened, but it really didn't. That means we made a false positive type of error. So this would be a type 1 error. So that would be a type 1 error. What would a type 2 error sound like? Well, a type 2 error would be we would decide that the average time on social media spent per day for American adults has not changed, but it really has, because that would be missing something. We think it hasn't changed, but it really has. That would be a type 2 error. Okay, so in this case now, you guys have seen sort of all the different cases of running one of these one sample mean hypothesis tests. In the first video, you guys saw how to do one where we were testing for an increase. In this video, we saw one how to test for a decrease and how to test for a change. In the next video, we'll continue to do maybe one more example of this procedure, but we'll also introduce another important part of inferential statistics, which is estimation. Right now, everything we're doing is about gathering evidence, but we'll also introduce an estimation technique called a confidence interval.